I am Siim Pikker, associate professor of micro and nano optics, which has not much to do with wood at all. But we come from, with Martin Timusk here also, we come from the Institute of Physics from Tartu, and our group background is nanostructures and the physics of nanostructures. So we are familiar with materials, material processing, we are familiar with analysis of these nanostructures, microstructures, material analysis. Then we have experienced quite a lot of with numerical simulations and numerical modeling of systems and materials and the physical properties of it, strengths, optical properties, electrical properties, mechanical properties, acoustics nowadays also. And we have also a little bit experience with development of novel materials, and wood is an interesting, let's say, playground where, from our side and our view, innovation in the material sense can still be done, and there are some really interesting possibilities there. Also, one of our persons, Dr. Rünno Lõhmus, he is also a mechanical engineer, and he helps also to develop prototype engineering solutions for, let's say, sample material fabrication processes and so on. So we have such a little background. So here is very complicated slide with a lot of things that we do. We do microanalysis, so electron microscopy, scanning probe microscopies. We do numerical simulations. Here's a slide or animation of a wood drying kiln, which we did in cooperation with the Tallinn Institute of Technology from Tartu. Then there are samples of material research. We have here a material that changes from transparent to opaque thanks to material properties and microstructure and nanostructure. And this switch of transparent material to opaque material, that comes from temperature shift, and it's a very fast acting material. So we did a lot of nanostructures, microstructures, which sense, let's say, magnetic fields or electric fields here in that sense, which gives an optical signal. So we have then also developed, Martin mostly here, developed transparent glass which can be switched thanks to electricity from transparent to opaque, and that with a novel solution which was a spray coating method. So it was kind of a cheap method, but in the practical sense not viable, because it is a self-organization effect that happens there. It's very sensitive to humidity, temperature, vibrations, and so on. So in that sense, it was not practically viable. So a lot of research has been done on metal oxide foams, aerogels, stuff like that. So there is a history of let's say, material research. Now, a big part of it is that we want to understand materials also from the micron perspective, nanostructures, and so on, which wood has quite a lot, and a complicated one, and depends on the species and the treatment of it. And we now develop our electron microscopy system to we have a goal to be the best microscopists for wooden structures. So if it's nanocellulose, if it's lignin, if it's if you want to understand let's say glue adhesions on laminates and something like that from the microstructure here. So we plan to be the best in Estonia in the electron microscopy field. with wooden and wood-based materials. So at the moment, here's some later results which we are doing together with the chemists who develop new processes of delignifying pulp materials, producing nanocellulose, and also developing new materials based on lignin and nanocellulose compositions, and using them as glues. And we can look at the material, let's say, morphology in a quite small scale. We are talking here around, like, here we have the scale bar here, 500 nanometers, but we are looking at really small stuff. And very many times, the physical properties of the pulp materials, they start from the micro and nano scale. So to understand those. And so we started now, let's say, heavy work this year, because the financing of this TEMTA projects has been an interesting scheme. Nobody wanted to do real research last year because nobody knew if we really get the money or got the money. But now the research has started, and we, as we had not a lot of experience with wood and what to do with it, in the beginning we started from the literature, and in 2018 there was a very interesting article in the Nature magazine which dealt with densifying of wood. And turns out that you can quite cheaply make wood strong, a lot stronger than it used to be in the natural form, by removing some percentage of lignin, so the binding material, and by compressing it under heat and quite a high pressure. And the material that results has now a modified structure, so you don't have any more the open cells, but it looks like a solid material. And this material has now higher mechanical properties. So it's harder, it's tougher, and it's, let's say, stiffness. For example, when you normalize it with its density, their mechanical properties can be better than even titanium alloys. So the weight to strength ratios. And this is engineering wood. And for example, here's a strain stress curve of a natural wood. We are having here on the scale bar, here is 200 megapascals. If we look at the natural wood or densified wood, we see that the mechanical properties increase quite a lot. We are talking about here strength increased up to 12 times in this article and 10 times increase in the work fracture. They did also some ballistic tests on this, and basically one can produce almost bulletproof wooden materials with this densification. And this is where we started. We took that article as a, let's say, starting point for our research in the wood material field. And we started looking at the underused and undervalued woods that we have here in Estonia, and we wanted to look at some species, so alder and aspen, for example. Aspen is a really fast-growing wood, but it has mechanical properties which are not useful for a lot of applications, so you do not do a wooden parquet floor out of aspen because it's too soft. But after densification, these are our samples here, we see that, for example, the Brinell hardness is increased quite drastically. We see here, this is untreated aspen, this is untreated alder, and then when we densified it, its Brinell hardness increased more than 10 times here for the aspen case. And here I have also now samples from this measurement. So this is the sample of aspen, which is not densified. So, and this is the same material, basically it was the same size, a sample was just cut off. But basically the aspen, the size of it should be like that, but after densification we get a little slice of it. So we densify it to densify 80% of it. So the material amount left is like 20% around that. But this material now is very much stronger. So and with the chemical modification it goes through, it's harder, it's stiffer, it's still lightweight, but basically one could fabricate parquets or flooring out of aspen if done the densification procedure. So in the sense of how tough will the material be, here we have the Brinell scale for different woods that are available here in Estonia. For example, here we have oak, which is around, like we have 4 here, which is more than twice harder than aspen in its usual form. But if you look at the densified aspen, then the densified aspen is around almost 5 times as hard. So the densification makes the material quite much stronger. We looked at what happens with the densification underneath the microscope. We have here the raw wood sample. We have here the sample where we have washed out some of the lignin, and this is a microstructure of the hardened and densified, I think aspen sample was this one image. We see that all the cell walls are crushed together. They have formed a monolith, which is way stronger than it was before. Then my colleagues also, together with the colleagues in Tallinn, are working on wood laminates and put in basalt fiber mats, and trying to understand what happens to these laminates, how does this lamination change their physical properties, are they getting better, these composite materials, are they stiffer, are they softer, do they hold on to the glue as good as they can. And we developed also testing now for some samples. We are trying to go to vibrational testing together with Terevare Observatorium, who tests satellite components on this sample, but we want to test wood samples and laminated wood samples. So we use this specially designed vibrational clamp, and we put vibrational sensors on top of it, and we want to analyze the laminate's physical properties and its durability using this device. Then we also do, Martin does a little bit of wood hydrophobic and wood treatment method development. Then some labs in our institute have done plasma research on wood. One of the main ideas here is that, for example, thermally treated wood, and probably also this densified wood, which is also thermally treated in some sense, they do not have a good adhesion with paints, glues, and one needs to increase the adhesion between the treatment layers and the wood itself. And here Plasma treatment has been shown to mitigate some of the effects, increasing the adhesion in some cases. Now it depends on plasma type, the gas type that you use in plasma, and I don't have time to speak about that. And another group also developed, who develops thin film methods based on atomic layer deposition. They also treated wood samples for high-tech wood, so for space applications, and tried to understand if we can build wooden satellites. Then about this hydrophobic and antifungal treatment that Martin is developing at the moment, we have the samples which is based on alder here. So we have an untreated sample of alder, we have a treated sample of alder, and the novelty is that we want to grow, for example, metal oxides, which, for example, in the zinc oxide case can be antifungal. It also should increase improve the UV resistance of it, maybe also increase the fire resistance of the material. So the idea is that we are not just coating the sample with zinc oxide material, but we want to grow the zinc oxide inside the wood structure itself. Then we have this computational modeling thing that we are doing, and I do not have time to talk about that a little bit. Basically, what we did was we assisted one company to the colleagues from our core facility in physics simulations, CFP physics, which we are part of. The colleagues have developed and optimized stacking and ventilation geometry of a container-based wood kiln for firewood drying and wood drying. So we can help with these kinds of simulations also. And thank you from my side.